Hey everyone, Professor Dustin here, and this video is going to be a solution to this whiteboard steel beam. So in this sort of crazy looking picture, we have a steel beam being held in place by a crane. So there's like a chain or a rope or something up there being held in place by a crane. It's got a mass M of 2450, so I'm going to go right ahead and call that mass M. And we're given two angles. The angle between the horizontal and the beam is 15, so that's right here. And the angle between the axis of the beam and the cable is 63. So you can see that that's the axis of the beam, and this thing is 63. So this crane is like lifting one end of the beam, and the other beam is stationary on the ground. First thing we want to know is what the tension in the cable is. If the length of the beam is 6.5 meters, so I'm going to call that length L and just indicate on the figure what that is. That is there. We're looking for the tension in the beam, so the tension in the rope, so that's the first unknown we have. And then we want to know how much force and in what direction is the ground acting on the beam with, and I'm just going to put some question marks around there. So the idea is that this beam clearly has multiple forces on it. It's got a mass, so it has a gravitational force on it. It also has a tension force on it. But if you write out the free body diagram for this thing, I'm going to note that the ground is doing something. In fact, it's resting on the ground, so the ground is clearly in contact with the beam. So there is like, we might call it a normal force, and maybe I will in this problem. But the ground is clearly doing something on it. So this is the case where we want to use the conditions of static equilibrium to find the force of the tension and the force that the ground, or the pivot point, is acting on the beam with. So like I said, this is clearly a statics problem, so I'm going to want to get a good free body diagram here. And in fact, because this beam is both in linear equilibrium and rotational equilibrium, I'm going to want a picture of the beam, a free body diagram of the beam that shows where all the forces are actually acting on the beam, not simply acting at the center of mass. So there's my beam. The tension is up here, acting at that angle theta 2. Let's put that angle in there too, theta 1. There is a gravitational force acting on this beam because it has some mass. The gravitational force is going to be acting at the center of mass. That's what gravitational force does. That's why we call it the center of mass. It's also called the center of gravity. So it's going to be pointed right down there, Fg. And the ground is doing something to the point of rotation of the beam. So in this case, because it's sitting on the ground, I kind of feel like I want to call the upwards part of that the normal force, because it seems natural to call the upwards part of that the normal force. But of course, the beam could be sliding back and forth on the ground as well, right? So there could be like a force of friction. In fact, if you look at the picture, the beam would totally be going in towards the right if the crane really was lifting at that angle, right? Because it's not totally vertical, it's kind of to the right. So there's a component of the force to the right. So I'm going to go right ahead and just call that force friction. And I guess it's going to be static friction because I don't think the beam is moving in that way. Maybe I should be a little bit more careful and just call it FF, whatever. We know the ground is doing something to the beam because the beam is being held in static equilibrium. So the next thing I want to do is write down Newton's laws. I think before doing this, I'm going to get some angles on this picture, break up these forces into various components just because it's going to be a little easier if I can do that from the very beginning. So first, let's break Ft into x and y components. So that's going to be Ftx. Notice that the angles here are pretty crazy, but luckily the first angle is with respect to the x direction right there. So I can immediately write down that it's the same angle as right there up here at the end. And so when I write down the component in this direction, I'm going to be writing Ft cosine of the sum of theta 1 and theta 2. Right, it's pretty easy to see that that angle is the thing that I need for the x component of Ft. It's the total angle, and so I have that the y component is going to be Ft sine of the sum of those two angles. So let's go ahead and write down our Newton's second law. First, let's do the x direction. And actually, those are the only things that has to be broken up. Everything else is in the x and y direction, so it's going to be relatively easy to write down the rest of the forces. So I've got the complicated one, Ft cosine theta 1 plus theta 2. But actually, there's only one other force in the x direction, and that's whatever the ground is doing, the thing I don't really understand, but it's some kind of static friction force. And if this thing is in equilibrium, that sums to 0. Same argument in the y direction. And again, we have just one complicated force in the y direction, Ft sine theta 1 plus theta 2. Then we have an Fg downwards, so that's just minus mg. And then we have a normal force upwards. And that's all equal to 0. So what we'd like is to be able to use these two equations to solve for the force of the tension, which is what we need in part A. But if you start calculating the number of counting the number of unknowns, we have one unknown right there. That's the actual tension force we want to find. We have a normal force, which is unknown, and we have the static friction force, which is unknown. So we have three unknowns here. Now, normally, not normally, but in many situations, we would be able to say, oh, the static friction force is somehow related to like mu s times Fn, and we would be able to eliminate one of them, but we don't really know what the static friction coefficient is. We have no idea what it is, in fact. And so we're not going to be able to do that. So these two Newton's laws equations are not going to help us, even if we'd have to know something about the static friction force. So what I'm getting to is that this is a situation where we have to use rotational equilibrium as well as linear equilibrium. We need to sum up all the torques. Each force is going to contribute a torque. So I can write this as like the torque due to the tension, the torque due to the gravity, the torque due to the normal force, and the torque due to the static friction force. Those should all sum up to be 0. So this is going to be sort of complicated. Remember that each torque is Rf sine phi. So we're going to put that in for each one of those torques. But we can immediately say that the torque due to the normal force and the torque due to the static friction force are going to be 0. So these guys are both going to be 0. You can make that argument in several ways. The easy way is just like, well, forces that act at the pivot are not going to make the thing rotate. That's what torque is measuring, is how much of the thing rotates. These things don't help the thing rotate, so they shouldn't be in there. Also, the distance from the pivot point to where they are acting on the beam is 0. The origin in this coordinate system is right there. Normal force and static friction are acting right there, and so these guys are definitely not going to be in our considerations at all. So the next thing I want to do is just write down the sum of the torques. So this is going to be Rf sine phi for the tension, the distance from the point of rotation to where the tension is acting, that's L. That's Ft is the force, which we don't know yet, and then we want to take the sine of phi. I'm going to have to work out what that phi is, I think. And then I'm going to add to it the torque due to gravity. So that is going to be the length, which is L over 2. That's where the gravitational force is acting, m times g, and then sine of phi. And I should be a little bit careful here. Phi g, phi t. That's the next thing I have to do is figure those things out. And also, I put them both as positive signs. I shouldn't have done that, right? One of them is making it rotate in one direction. One is making it rotate in the other. It doesn't actually matter what you do, but you can work out using the right-hand rule if you want to do it carefully. R is right there along the beam. So if you take your right hand, you see that for gravity, you have to flip over your right hand to curl into gravity. And so Fg is going to be into the board with a negative sign. So I should have made this guy negative. I can't erase it anymore. That should be negative. And this thing should remain positive. Again, it doesn't actually matter as long as they're in different directions. You will get the right answer, but technically in that coordinate system that I'm using, the gravitational force is into the board and the torque due to the tension is out of the board. Okay, so the next thing is to make sure that we get the right angles in there. And so we have to remember that for that angle, you need to set the vectors up to be tail to tail like this, R and F. None of my vectors are set up that way, but it is pretty easy to set them up this way. So for instance, for the tension, this is the R vector. This is the R vector right there. So what I'm going to do is I'm going to take that vector and slide it up here. And then I can see that the angle between R and F is going to be that angle right there, and that is theta 2. So this guy is going to be theta 2. I have to play the same game with gravity. So I take R, slide it up. Sorry, I should change colors. Slide it up to right there. That's the version of R slid up, and what I should put into gravity is that angle right there. That's going to be theta g. So it's a little tricky to get that, but it's not so hard because we have a triangle there, which I'm going to draw down here. So the triangle is that's theta 1. and that's then 90 minus theta 1. So the angle makes a straight line like that, theta g, and so it's 180 minus 90 minus theta 1. That is 180 minus 90 is 90 plus theta 1, because those two signs there cancel. So this is going to be 90 plus theta 1. Okay, so I've now manipulated the torque equation, I hope enough to solve it. Let's just check. I know the lengths there and there, that's just L over 2. I know the angle here, I know this is 90 plus theta 1. I know mg, so really it's just a matter of getting ft. I think I'm going to have to move this onto a new page. Okay, so there's my free body diagram and the equation that I used to find the torque, and now I can just solve this for Ft. I'll do this in a couple of steps. First I just have LFT sine theta 2, and I'm going to move that other thing to the other side, so this is going to be L over 2 mg sine 90 plus theta 1. Then I have L's on both sides, so I can cancel those. And then I just want to divide by, looks like sine theta 2. So Ft is just going to be mg sine 90 plus theta 1 divided by 2 sine theta 2. Great, now I can plug that into my calculator. And I see the answer is about 1,300 newtons. If you go to my solutions, you'll see that I use a little trick. In my written solutions, you see that I use a little trick here, which is that sine 90 plus theta is related to cosine in this following way, cosine theta 1. So you could replace sine of 90 plus theta with cosine theta. It's nice to know those little 90-degree shifts to make trig identities a little bit simpler, but it doesn't really matter. You could just do 90 plus theta 1, the sine of 90 plus theta 1, or the cosine of theta 1. You get the same answer. So that's the answer to part A. The tension in the cable is 13,000 newtons. So if you recall, part B is then how much force and in which direction is the ground acting on the beam with. So then let me pull in my Newton's second law that I had on the previous slide. So there's the sum of the forces that I had, and so recall that the reason I had to use the torque equation is because I had 3 unknowns. But now I actually have only 2 unknowns because the tension force has been found out. We know how big Ft actually is. Also notice the question we're being asked here is how much force and in which direction is the ground acting on the beam with. When we calculate the static friction force and a normal force, okay, the static friction force and the normal force are connected to each other through the coefficient of friction, but we're just trying to find the forces, so I can just immediately solve each of them in each of the 2 directions. The static friction force comes from moving this guy to the other side. The static friction force is just equal to the tension force times the cosine of the sum of the angles. And the normal force is simply the gravitational force minus the Ft times sine of the sum of the angles. So in this case, the normal force is smaller than the gravitational force because of whatever the rope is doing is helping to hold the beam up. So if you go to your calculator and calculate the static friction force, that is going to be 2,700 newtons. The normal force is going to end up being 11,290 newtons. And then this problem is actually asking for how much force, so I could accept that as an answer, but also we want to know what direction, so let's just calculate the magnitude of the forces. Notice that in this special case, the static friction is in the x direction, so I can just use that as the x direction. The normal force is in the y direction, so I can just do that, and that total force is 11,612. 11,612 newtons, so that's the magnitude of the force, and then the direction of the force. Well, I have to be a little bit careful. It's clearly like going upwards and to the left. And actually, the signs won't be found in these expressions because I assumed that the static friction is going up and to the left that way. So I can find that the angle of these forces by doing that, and then saying what the angle that I want to find is that guy, call it like gamma or something. And now I can write that gamma is the inverse tangent of the opposite, which is going to be the normal force, divided by the adjacent, which is the static friction force. And if you plug that into your calculator, you get 76.5 degrees. So this is a pretty involved problem, mostly because of this last step. We've certainly done in class finding the tension on a string. This one's a little bit tricky because you have this additional angle, so you have two different angles in the two places of the two forces, but only a minor sort of variation on theme that we've done already. The additional part here is finding the pivot force on the beam, which makes this problem relatively involved. But a lot of statics problems are just like this. You just have a bunch of algebraic equations, and you just got to hack through them. That's just kind of life for this topic. Okay, so that has been a solution to the steel beam whiteboard problem. Hope it has been helpful and clarifying. Thank you for watching, and I will see you next time.